Welcome to lesson 6.2 on logarithms. If you'd like to follow along, you can find that on page 323 in your textbook. Now, logarithmic functions are the inverse of exponential functions. What do we mean by the word inverse? The word inverse pretty much just means to undo something. So for instance, we have other functions that are the inverse operations. We have other operations that are the inverse of each other. For instance, addition and subtraction. If I have the number 5 and I add 2 to it, the result will be 7. If I want to get back from my 7 to my 5, I need to undo this addition operation. 7 take away 2 equals 5. Subtraction undoes addition. Subtraction is the inverse operation of addition. There are other inverse operations. Multiplication and division. 5 times 6 equals 30. And if I want to undo this and get back down to 5, I can go 30 divided by 6 equals 5. Multiplication and division are inverse functions. Well, why do we need an inverse function? Inverse operations. Why do we need an inverse operation for exponential functions? Suppose a new website becomes very popular very quickly. The number of visitors as a function of time can be modeled using an exponential function. So this is over time, the number of visitors visiting the website can be modeled as an exponential function. Using a graph like this, it's very easy. This is in the form y equals b to the power of x. It would be very easy to sub in a value of x and use it to determine how many people were on the website at that time. However, it's difficult to determine at what time a certain number of visitors had reached the website. And so to do this, we can use the inverse of an exponential function, which is logarithmic functions. Now, in an exponential function, it's also easy to see that every value of x has a unique y value. This is also true of logarithmic functions, which is what makes them functions, really. Let's explore the relationship between exponential functions and logarithmic functions a little bit more closely. We said already that logarithms are the inverse of exponents. For example, we could take y equals 2 to the power of x. Let's explain this a little more thoroughly. The exponential function says y with base of b, y is equal to b to the power of x. For an inverse function, we really are just swapping the x and the y. So the inverse of y equals b to the x is x equals b to the power of y. But in math, we don't really like things in the form where x is described in terms of y. We'd much prefer having y described in terms of x, where y remains the dependent variable and x the independent variable. And so we can write this b to the power of y equals x as, we can write this as y equals the log of x to the base b. Y equals the log of x to the base b. So, a final note. The logarithmic function is defined as y equals log of x to the base b. And we can write that in words. Y equals the logarithm of x to the base b. And that's how you read this little mathematical sentence over here. The function is defined only for values of b that are greater than 0, and b cannot equal 1. Defined only for b greater than 0, yet the restriction b cannot equal 1. Let's see a couple examples of this. Let's say we have the equation 2 to the power of 3 equals 8. We know that to be true. We can rewrite this in terms of logs. This is where 3 becomes y, the base is 2, and x is 8. So in this case, we have the log of 8 to the base 2, base, is equal to 3, which in the original equation was the exponent. Good. Let's try another one. 5 to the power of 2 equals 25. Then the log of 25 to the base 5 is equal to 2. Again, we're the remaining, the value on the right side of the equation was our exponent, and the base is still our base, and the log of 25 to the base of 5 is 2, or 5 to the power of 2 equals 25. Let's see another one with variables. We have r to the power of s equals t. This is the exact same as saying the log of t to the base to the base r is equal to s. Y here is called the logarithm. So the logarithm y is the exponent to which the base b must be raised to give the value x. So b is raised to a certain exponent, and it gives the value x. Y is that exponent. Okay, looking at example 1, we're asked to write an exponential equation in logarithmic form. So we have in A the equation 16 is equal to 2 to the power of 4. Now we're remembering that when we write it as a logarithm, we're identifying y. Is the logarithm required to bring the base b to equal the value of 16? 4 equals the log of 16 base 2. C, 3 to the power of negative 2 is equal to 1 over 9. This time we're going to write the logarithm first. The logarithm of 1 over 9 to the base 3 is equal to negative 2. And all that means is if we have the base 3, we want it to equal 1 over 9, we need to raise it to the exponent negative 2. Example 2a is the log of 81 to the base 3. And we're asked to evaluate this. What we need to remember is that the logarithm is the exponent to which you must raise a base to produce a given value. So what we're really finding out here is we have this base 3, And we want to know what value, what exponent do we need to raise this to in order to get the value 81. Now, 81 is simply 3 to the power of 4, right? 3 times 3 is 9, times 3 is 27, times 3 is 81. So here we have 3 to the power of 4, which tells me that y is equal to 4. B says that we're going to evaluate the log of 1 over 8 to the base of 2. So what exponent is necessary to bring this base 2 to equal 1 over 8? Well, I have a little clue here. The 8, I know 2 to the power of 3 equals 8, but now I have 1 over 8. So if I know my rules of exponents, I know that 1 over 8 is equal to 1 over 2 to the power of 3, which is equal to 2 to negative 3, which tells me that the log of 1 over 8 to the base of 2 is equal to negative 3. Example C asks us to evaluate the log of 1/100th to the base 10. So we can let y equal this log, the log of 0.01 to the base of 10. Then, since this is true, 10 to the power of y is equal to 0.01. Remember that the logarithm is the exponent required to raise the base to get the value of x. Well, 10 to the power of y here is equal to 0.01, which is 10 to the power of negative 2. So we have here that y is equal to negative 2. One thing to notice in this special case is that the log, that's off the screen, that the log of a to the power of b to the base a is equal to b. That might sound confusing, but if we look here, that's what we have. We have the log of 0.01. Well, we said that we could write that as 10 to the power of negative 2. So now we have the log of 10 to the negative 2 to the base 10, and that was equal to negative 2. And that's just what we have here. A and A, A and A, B and B, B and B. So there's a connection that we can use there as we work with these logarithms in the future. Now, because the modern number system is a base 10 system, logarithms to the base 10 are called common logarithms. Common logarithms are logarithms to the base 10. Now, when we're writing common logarithms, that is any logarithm to the base 10, it is not necessary to write the base. What that means is that the log of 100 is understood to mean the same as the log of 100 to the base 10. So whenever we're working with the base of 10, we do not need to write the base. We can simply write it as log 100 or log whatever value you are hoping to raise the power of 10 to. Okay, example 3 asks us to write a logarithmic equation in exponential form. So I have a here, the log of 64 to the base 4 is equal to 3. And if I need to go back and see how my logs relate to my exponents, I can do that. But we need to remember that here the base is 4, the exponent is 3, and so in exponential form, this equation is 4 to the power of 3 equals 64. B says y equals the log of x. Now, because there is no base written, this function is understood to be in the common logarithm of x with a base 10. So in exponential form, this is 10 to the power of y equals x. Nothing too tough there. Okay, we said that using logarithms would help us find the exponents of certain exponential functions, and that's true, but it's much easier when we're working with whole numbers. Well, what if the exponent isn't going to be a whole number? Let's look at example 4. A of example 4, we have the log of 10 with the base of 2. So what we would need to find out is the exponent, to which we need to raise the base 2 in order to result in the value of 10. Well, I know a couple of things. I know that the log of 8 to the base 2 is equal to 3, because 2 to the power of 3 equals 8. I know that the log of 16 to the base 2 is equal to 4, because 2 to the power of 4 equals 16. So the log of 2 to the power of 10 lies somewhere in between 3 and 4. At this point, I'm going to do some guess and check, some estimating. Okay, well, let's try an exponent of 3.5. So I've got 2 to the power of 3.5. Well, that equals approximately 11.3. Too high. Let's try a lower value. Let's try 3.1. 2 to the power of 3.1 equals approximately 8.6. Too low. Okay, 3.3. 2 to the power of 3.3. We should be getting a little bit closer here. I plug that into my calculator. I result with 9.8. I'm getting closer. Need to get a little bit higher with my value of y here. So let's try 3.32. 2 to the power of 3. Oh, I'm off the grid. Okay. I'm going to scroll up. 3.32. 2 to the power of 3.32 equals approximately, if we round it to one decimal place, 10. And this is a good estimate. Therefore, the log of 10 to the base 2 is equal to, or approximately, 3.32. Another way, of course, to do this would be graph. You could graph y equals 2 to the power of x, and you could trace the graph of y equals 2 to the power of x on GSP in order to find the value of x that produces y equals 10. Another way to do this would be on your graphing calculator to find the intersection of two functions. Again, you would graph the function y equals 2 to the power of x. You would also graph the function y equals 10. And wherever those two lines, wherever the line and the curve intersect, it will give you the x value of 3.32 ... And so there's three ways there to find the approximate logarithm. One quick and painless way to calculate the logarithm of something like we have here, is to simply take the log of x, which is 10, divide it by the log of your base. You can put that in your calculator, and you will right away come out with 3.32. Let's try that method here. Here we have the common logarithm, which is 10, base 10. So we can just say we have log of x, which is 2500, divide that value by the log of 10, and this approximates at 3.4. All right, that is lesson 6.2. You can go ahead and find your homework there on page 328, numbers 1 through 10, 13, and 14.